Okay, everyone, I think that we can start now. Thank you for coming today. And today we have Julian Straus from the Department of Chemical Engineering, who is going to talk about parallel computing with MATLAB. So, without further ado, please, Julian.
Thanks for the short introduction. As mentioned, my name is Julian Straus. I'm a third-year PhD student in the Process Systems Engineering group, and that implies that I do a lot of simulations and a lot of modeling. And my research is focusing, or for my research, I have to do a lot of simulations which are essentially independent, just initial values change. And that is where 1.5 years ago I got into, or 1.5 to 2 years ago, I got a bit into how you could parallelize stuff using MATLAB, and I'm using that now, at least parallelization extensively, GPU computing from time to time. And this talk should give you more short introduction about what is possible and how you can do that stuff. For detailed analysis, especially, or for detailed introductions, so especially if you want to go into cluster computing, it's wise to take a look at the webinars of MathWorks. They are generally quite good. The talk is structured as follows. First, I'm going to introduce what is meant with parallel and GPU computing. Then I shortly go into the direction why we should use it and when, because not all the times parallel and GPU computing actually give you an advantage for your simulations. I will talk briefly about general requirements and then explain directly in MATLAB how you can use parallel computing with the built-in functions, and how you can write your own functions for parallel computing. Then I will move on to GPU computing and finalize with the conclusions. And for myself, to start already how I see it for myself, that parallel computing is really, really powerful. It can't be used for each problems. I use it a lot. GPU computing still is a bit limited by functions you can do. If you do not want to write libraries yourself, then it's still a bit to go with that. So let us first start. What is parallel computing using a CPU? And to go in this direction, we have to go first back into what a CPU is, or how it is built up. Nowadays, consumer CPUs have about 4 to 8 cores. If you buy a computer which is really cheap, you end up with only 2 cores. Most of the laptops have 2 cores. Each of these cores have a so-called cache, and together they have a shared cache. So you could imagine it like this is a whole die. So what is inside your computer? You have core 1, 2, 3 with their respective caches, and a combined cache and an interface. You probably will ask yourself now, what is a cache? Cache is pretty much a fast internal memory. So the connection from a cache to the core is way faster than the connection from the CPU as a whole unit to the memory. It is important to know these concepts because these are points where limitations can grow, where parallel computing is not good anymore. In cases when data transfer is too much. And the sizes generally are quite small. I wrote now here for my CPU in my processor at home. But for standard small matrices up to several thousand elements, that is sufficient. If you go in big data, you easily end up with matrices of size of several hundred megabytes, even in the gigabyte range I had. And the core concept now of parallel computing is that you compute each of these cores get a dedicated task and reports when the task is finished back to the interface. So in this case, you distribute work among all of these cores and gather the information back. So for a CPU, it's generally quite simple. The highest number of independent cores, I think, is now in the range of 12 to 16 cores. If you have clusters, obviously you can have infinite number of cores. Well, not infinite, but a very high number of cores which you should utilize. GPU computing is something else. Now, how many of you do know what a GPU is? Okay, it's written there. Simple. It's a graphics processing unit. So it was initially introduced for rendering frames, quite a lot for playing computer games, also for video editing, and they are specifically designed for this task. They have hundreds of cores. That is why people started to think about using them as well for calculations. The Tesla P100, which is based on the latest NVIDIA GPU generation, has, for example, 3,500 cores. And 3,500 cores compared to 12 cores in a CPU, that is kind of a huge difference. The big issue in the beginning was you did not have a nice interface, how you could use the GPU for calculations. And in 2007, so just 10 years ago, NVIDIA introduced CUDA. NVIDIA is a manufacturer of graphic processing units. There are others as well. And CUDA is solely for NVIDIA. But later on, OpenCL was introduced as an open standard, which is also kind of an application programming interface between what you want to write and what the GPU gets. And through this introduction, it allows us essentially to use code in C, C++, Fortran. You can run that because of CUDA and OpenCL on GPUs. And that makes it possible for us to utilize a GPU for doing the calculations for us. This talk now will only focus on CUDA, because MATLAB itself does not support OpenCL. And quite a lot of programs still support CUDA, the NVIDIA, but not OpenCL. So if you want to buy a GPU for calculations, you still have to limit yourself for CUDA or NVIDIA cards. So why do we want to use parallelization? It's pretty much simple. If we can utilize all of our cores in a CPU, we can speed up the process quite a lot. Normally, a theoretical threshold is the number of cores. That is how you can save. Or for example, a quad core can go down to 25% of the time. Most of the time you don't get there because you have other limiting steps, but it can theoretically go in this direction. And if you use now your computer using MATLAB without anything parallelized, you see that you can still work nicely with it in parallel. That means the calculations do not take the whole computer, and that is something I, for example, do not want to have. If I have calculations running overnight, I want that actually they are finished as fast as possible, so I can work in the next morning again with the computer nicely and rewrite code. So you can actually utilize the computer in the entireness. And if I'm not sure whether you do that. For myself, I don't work with clusters, mostly because I need also only Microsoft available commercial software, and the interactions that gets a bit screwed over. But if you want to use a cluster, your code has to be in some way parallelized. Otherwise, you won't gain anything. Clusters normally have, or also supercomputers, that's working differently, but they have the frequency of the CPUs in this case is smaller than on the consumer product, but they just have a lot with really fast connections in between. So without parallelization, you do not really benefit from that. However, that is a big point. Parallelization is only necessary if the simulations take a lot of time. If they are not, then there's not a problem. And the biggest point is they have to be parallelizable. Not everything can be parallelized, mostly because of dependencies, and to that I come later. As a rule of thumb, based on the origin of GPUs and CPUs, a GPU you want to use if you have hundreds or thousands of really small mathematical operations, multiplications, additions, and so on, that is something GPUs are really, really strong at. But if you have, for example, ODE systems you want to solve, which take each ODE half an hour and you have different initial conditions, then you want to go parallelization on its CPU. Because in this case, CPU parallelization is a thing which benefits most from. So, what is a general requirement? When can you actually use it? The one important thing, and which is always true, that the calculations you want to have or you want to do have to be independent. So for example, if you have loops, or it cannot depend on something which, or no, you do a calculation on the one CPU, one core, and the calculation on the other core needs something of this core, that is not going to work. So they have to be independent. As said beforehand, especially if you have a lot of simulations with different initial conditions, you can benefit. If you have other simulations, which I will later have an example as well, you do not really benefit from it. And it requires you to write a code in a certain way. Especially in MATLAB, you can't use the whole library. How you can want to work with it, you have limitations. For one important thing as well for performance is that you want to reduce communication. And additionally, if you have dependencies, if possible, you want to remove them. And the most important part there is check whether the functions already utilize parallelization. MATLAB itself is built in a way that it, for a lot of calculations itself, it utilizes all your cores. So a lot of these built-in functions already are utilizing all cores. They are multi-threaded in this situation, it's called. So it distributes independently to the work to the different cores. That includes singular value decomposition, principal component analysis, convolutions, Hardeman product, matrix product. So quite a lot of things. And it's wise to check, is it parallelized what I want to do already? Because then you don't gain anything and even lose time. So if I take a look at that, how can I check whether something is parallelized? Simplest way is going to the resource monitor. That is really the simplest way. In the resource monitor, why don't you want to work anymore? Doesn't matter. I hope it's visible. You see here the cores, and you can see how much is utilized at this point. And obviously you want it to be 100%. I won't use the resource monitor. I'm going to work with a different program which is called MSE Afterburn, which is for that better, because here you can see it nice better in real time and you have an overlay. But that is something which is just personal preference. So let's see whether our stuff already utilizes parallelization. Here in this case I use a principal component analysis, big data stuff with a 3000 times 3000 matrix, which is roughly I think about 74 megabyte. But don't put anything on it. If I run it, what we can see directly, the core utilization here in the red for core 1, 2, 3, and 4 goes to 100%. And then when it's finished, it drops to the idle state of 27%. So pretty much we can see with that, it's already parallelized. The same accounts for a lot of different functions, as said, matrix product, Hardeman product, and it's something where you can get the information. Does it help me to parallelize it or not? For example, if I go now instead to a fast Fourier transformation, in this case I do it with a for loop, because I just want to show you that for a longer period that it's not utilizing all cores, and if I run it, you see its total utilization is at 70%, 60, 59%. So in this case, parallelization actually gives me an advantage. So that is a simple case where you can see parallelization helps. So in a lot of cases, MATLAB does it automatically for you. You don't have to do anything, fine. And that is also the reason why everyone tells beginners in MATLAB that they should write everything in matrices instead of in loops or instead of using functions. Because if you have the matrices, multiplications and so on, then you use all cores. A second point is where MATLAB makes it really simple for us. In a lot of cases, you can just, for a lot of functions, especially in the optimization toolbox, you can just say, use parallel, and it does it for you. So, for example, if you want to solve a nonlinear system of equation, or you want to optimize and solve for the KKT conditions, you pretty much always have to either provide gradient information, or let MATLAB do it with finite differences. And finite differences, depending on how many variables you have, can be really, really time consuming. So if we take a look at that now, this is a function which I use for myself. So I just run it to show it. Part of my code, if I want to use it, I have to define an options case in MATLAB, where pretty much I define for which solver, and then I can have a lot of options I can feed it. I just go for display off because I don't want to have the solution display, but sometimes it's really nice to have it on. If I now run this system without parallel computing, it's a 442 states system. So I have to calculate 442 gradients. If I run that, first of all, we see utilization in total is 30, 40%, 30%. So pretty much what it does while doing all these simulations, it does not use all cores, and it takes 12 seconds, 12.6 seconds, because of the evaluations of the system. If I now take, if I want to use now parallelization on it, it's quite simple. Use parallel in the options block structure, true. In this case it's true, in other cases it's yes, no, but you can always find that out in the help functions. And if I run that, I first have to start a parallel pool, which I forgot. The timing will be a bit off because of that. We can see it goes directly to 99–100% of utilization. Don't look at this number, that was mostly because it had to start a parallel pool. Let's run it again without that. Necessity to start a parallel pool, 5 seconds. So I save a factor 2 roughly. It's important to notice the computer I use for that is a quad core. So I save a factor of 2 for a quad core. Theoretically, I would have saved factor 4, so you do not gain that much. And in this case, do I have it here? No. If I have each evaluation of my system each evaluation of the function I provide, the anonymous function I provide to the system, takes about 9 milliseconds. And that was what was tick-tock timing, so it's a bit unsecure, but just give you then an idea, if I have a function evaluation that short, I gain already a factor of 2 for parallel computing. The second thing, or where I use it personally, is the neural network training. In neural network training, you also have a lot of calculations which you can parallelize. And if we assume we have a simple cascade forward net, just one hidden layer, 10 hidden neurons. If we want to train that from a function A to B, the function is net train A to B. And here, it's the same thing, you have to append, use parallel, but as MATLAB is somehow not synchronizing the commands how you should use it, it's yes. It's not true, it's yes. But these things you always find inside MATLAB. Point is, you can gain with that some parts, and these things are really, really easy to implement in your code. If we now move on to a bit more complicated thing, we can parallelize for loops. That is pretty much the thing MATLAB easiest allows us to parallelize. And the command for that is quite simple. It's par4, parallel for loop. Par4, for par4 or parallelization, you can classify variables into 5 different types. And that is also true independently of which language you use. You have the loop variable, which is just, I mean, you have in a for loop you have for k from 1 to 100, for example, and then k is a loop variable. You can do quite a lot of things with that. You can use it mostly for indexing, for multiplications. Important is the loop variable, you won't have it after the par4 loop, so you don't get a final value out of that. Second thing is a slice variable. Normally, if you want to parallelize stuff, you want to do a lot of simulations with different initial conditions or different parameters. In this case, in each iteration, you only need from your parameters matrix only a small part, and that is a slice variable. In this situation, you save bandwidth, you save time for the transfer of these matrices to the core and back, and they are pretty much all input and output variables. You have broadcast variables, and broadcast variables are variables which are broadcast through to all the loops. So if you do not do that correctly with a slice variable, you end up with a broadcast variable, and then you have communications overhead, which drastically slows down the calculations. So that is something where one really has to be careful. We have reduction variables, which can be accumulation or reduction of a certain variable, but it is important that that is completely, or what you do with that is associative. Because if it's not associative, then you get wrong results in the end, because then it depends on the calculation order. And finally, we have temporary variables, and these are only variables which are inside the loop, and they are not afterwards available outside the loop. So be careful whether you define something as temporary variable. Now, taking a look at a really simple loop, this one is just some dumb stuff I made up, not really necessary to be used. Loop variable in this case is k. It goes from 1 to 10. So the k is used partly for multiplications, partly for taking something out of sliced variables, and also in an if loop. You can do whatever you want with these ones. The sliced variables are b, because here we access bk and out k. Sliced variables can be cells or normal arrays, but it cannot be a cell or an array inside a structure. So there are some restrictions on what sliced variables can be. Broadcast variables, in this case, is e, and broadcast variables are not changed inside your loop and do not get outside of your loop. Or you can change them inside the loop. Think you can, but generally they are not transmitted outside. It's only to all together. Reduction variables in this case is c. So in c I just have a addition of something else to it, and that is completely associative, so we can use it that way. And temporary variable is d. It's in this case not necessary, but it frequently helps you to simplify the understanding of your code. So I use them as well, because it makes stuff simpler. And if we now take a look at that same example, if we run that, I predefine the reduction variable and the temporary variable, and if I run it, it pretty much works as expected. And important is, let's get out of this. The k, if I try now to access k, which is my loop variable, and because I want to do something with it afterwards, it's not defined. It's only defined internally in your system. So if you don't have a final k, so if you want to have something which is counting how many iterations you have, you need to have a reduction variable where you just add always 1. So you don't have access to that. The temporary variable d here, I specify in each loop. I also specified it beforehand as equal 3. Not necessary, but if I now go for this variable, it just gives me what I specified beforehand. Yeah, and the c ends up to be 60, and that is if k is a multiple of 2, or the remainder or the modulus of k and 2 is 0, then it adds k times 2. So 4 plus 8 plus 16 and so on, ending up to be 60. And then you get the final value for that. Now, if I want to change something and use bk, plus a minus bk minus 1, it will tell me that something and said, now the entire structure of b is a broadcast variable, which is in this case not complicated. I only have 10 variables, but you have to be careful with that. So you should define a new array where you have b and b minus 1 in, for example, a row or in a column, and then you transfer only that. In this case, you don't have a broadcast variable anymore, and you reduce overhead. More importantly, if I say out k minus 1, it also complains, because now I have dependencies. It's not going to work anymore. So let's see how that gives us advantage. That was not where I wanted to go. What that gives us advantages. I'm looking now again of something which was already, I said before, I'd never parallelize something which is already parallelized. So I'm looking here at the convolution, the two-dimensional convolution, and see what happens if I use a par for loop in the bottom or a for loop for, how many is it? 50 convolutions for 50 different random matrices. And if I run that, first of all, we notice CPU goes directly to 100% in both cases, and the inherent parallelization of MATLAB is faster than using the par for loop. So if you have only matrix multiplications or something which is already parallelized, there's no point in using par for. If, on the other hand, you have more complicated calculations, and in this case, the complication, it's a more complicated thing which is not parallelized by MATLAB itself. In this case, it's just a simple pause for 0.05 seconds. It's easiest to implement. If we run it now, the CPU won't go to 100% because of this pause after each of this iteration. But that is not what I want to show you. You can see now, I hope it's also, let's put it to the top. As we can see, we are now at 60% of the time compared to beforehand. So if we have something which is not parallelized by MATLAB and all, in this case, a simple pause, then parallelization can give you an advantage. Now looking more into a real application, going back to the system I had beforehand. I even had it here. In this case, I have, I just run it, how many is it? 500 times, because I can't change initial conditions inside a for-f solve directly. You would need to write a different function. And I provide, in this case, the Jacobian, because we do not want to wait always the 13 seconds for each solution. So I just provide the Jacobian, I wrote it down, it's quite simple for this system. And if I run that, now I have to restart this. If I run it the 500 times of this simulation, we can see our CPU is not really entirely utilized, and it takes, do not require, I think something like 15 to 20 seconds. Yeah, 18 seconds. So it was a quite good guess. Now if we instead have a par for loop, see, if I have here, beforehand I had a structure as something written out. If I have a structure, it's not going to work. So I had to go for just A. And I just simply use a par for loop. All the other options are the same, not changed. Utilizing all 4 cores, we can see that it goes to 100% up. And it takes 7 seconds, now in this case. If I run that, I can also define how many cores it should use in a par for loop, and that is quite simple. You just add another value here, L in this case, which is just the number of cores I want to use in a par for loop. For example, yeah, do not think a point why you do not want to use maximum, but you can do that. And if I run that and take a look how it comes out, I run now from 1 core with a really low utilization. So we have to wait the 18 seconds again. 2 cores, we can see for core 4, it pretty much is way more utilized now. Takes 9 seconds. Now we are at 84%, another step going in the evaluation. 6 seconds, and now at 100% it takes 5 seconds. That's why this 7 seconds here before, and if you run it the first time in MATLAB code, essentially if you want to have full speed you have to run it multiple times, because every time you restart it, it yeah, creates new max files for that. And not max files, but creates new for itself for the calculations. But we can see now in this plot the actual speed up, which is the circles, squares, and the theoretically attainable speed up. So in each case you will at one point go to bottleneck, and then using more cores does not benefit that much anymore. And as we can see, 2 cores still quite good, 3 cores close, 4 cores not that much. So for long-term evaluate or long-term runs, I pretty much end up with how much is it? 30% of the time with using 4 cores, which is in my opinion quite nice to have. So now we can, as you see, achieve quite a lot already with a CPU. Why do we want to use a GPU? And these are performance plots I created on my own computer at home. This one is the read and write bandwidth. Blue is GPU, red is CPU. One can see that the CPU peaks at around, how many array size? 2. Now I have to check again. 200 kilobyte. So 200 kilobyte, we have a peak and read and write of the CPU, and then it pretty much levels off. This one here is a megabyte, and that corresponds pretty much to the size of our caches. So the more we need read and write, or the bigger our array is, the more and more the GPU excels. So for small calculations, you do not get such a benefit. But as soon as it gets to big calculations, it goes crazy. And this one here is for double precision matrix multiplication, and it's gigaflops, which is just a measure of giga floating point operations per second, and we end up at a factor 2 in double precision. So we can improve our calculations even further. And for GPU computing, it is really, really fast when it's not mathematically complex. And it has also really fast communication between the graphic memory and the GPU, and a smaller between the memory and GPU. The connections or the communications, as far as I know, between graphic memory and GPU is faster than the one between CPU and memory. So there's something to gain out of that. And the nice thing here is a lot of the core functions in MATLAB, which essentially all the other functions are built on, are available in GPU computing. And the only simple thing how you can do that is using the command GPU array. You can do that in multiple ways. Simplest one is you define a matrix. Here 1 million double precision values and just GPU array of the matrix. Disadvantage in this case is you have that in the memory. If you don't want to have it, you can directly define it as an additional point. And if you don't like that either, you can write it as a structure call, GPU array.rand. And all what this GPU array is doing, it transfers from the main memory or creates in the GPU memory. In this case, it transfers it, but it's still kept in the main memory as well. In this case, it just creates something in the main memory. And if we now take a look at that, let's say A equals, let's make it simpler. So define A as a GPU array of a random number, and it's there. We can write it like that. Gives us the same, or works as well. The nice thing about, I have way too many in here. If we take a look now at this, if you just take a look at how it is defined, is it actually visible in the back? I checked it beforehand, and 200 times magnification was partly doable. We have A now as a matrix, 1000 times 1000, as a class GPU array. GPU array allows single and double precision, quadruple precision, I'm not sure, but honestly, who uses it? And it still needs some part in the memory, 108 bytes, and it's mostly, as far as I know, to get where it is. So MATLAB knows it's existing. But if I now instead write a whole matrix inside the normal memory, it's 8 million bytes, 8 megabytes for 1 million element matrix. Because each matrix obviously is, each value is 8 bytes. So, but let's see what we can do with that. As said, it's generally quite simple to implement GPU calculations inside your code. In this case, I go for a singular value decomposition, which is readily available. And the only thing I have to do is A2 equals GPU array of A. And as soon as I've done it, it knows it. what we can see, singular value decomposition goes up to 100%, takes 5 seconds. This now, top one is my GPU. So if I do a singular value composition, GPU is in the range of 70%. Problem is, CPU is also in the range of 70–90%. So in this situation, a lot of the calculations are both on the CPU and the GPU. So we actually are slower with GPU calculations. Does not necessarily gives you such a huge benefit. It's always a question how much is on the CPU, how much is on the GPU. On the other hand, if I go for a matrix product, which I just do again 500 times, because I wanted to go for smaller numbers. If I run that, first of all, we see it's close to 100% on the CPU, so it's reasonable with the internal parallelization. Taking 10 seconds. Let's see what the GPU is doing. Now, here we can see 100% GPU usage. Drops down, took 4.9 seconds. So this is also what you saw before in the double precision plot, the gigaflops for GPU calculation and matrix multiplication. That is something really simple to be done, a matrix multiplication. So that is something GPUs excel at. Now, when you get your results, they are written in the GPU memory. You can't do anything with that. All with that you use these results for, all the calculations will be in the GPU. For that, the command is quite simple, gather. With gather, you just collect everything, or collect this array from the GPU into your memory. So it works simple. So GPU computing in this case is really, really simple. Now, as another example, I took the liberty of using the MATLAB example, the Mandelbrot set, which is quite famous, and it's quite simply defined. So it's a set of complex numbers which, if you add them, take the product and iterate on this part, if n goes to infinity, the absolute value is smaller than 2. So pretty much in this case, as we can't go to infinity, what we have to do after each we have iterations and a for loop. We do matrix multiplication or in this case Hadamard product, so element-wise multiplication and addition, and that we do for a really, really long time. That is quite simple to write mathematically. Your complex number is, or they initialize it with a set 0, which is your complex number. And then you just define maximum number of iterations, and for each of that, element-wise multiplication, addition, then you check which one are smaller or equal than 2, and then you just increase the counter. And the counter tells us how it develops over the course. Essentially, you only need to do that in the end, to check in the end, but this way you see how it develops. Now, can we use, I mean this one is inherently parallelized, but can we use a path for loop? Any ideas coming out? Pretty much no, because it's depending here, the calculation is depending on each iterations. So you have to go for the previous one, so it's not going to work. So it's a MATLAB example, and I'm just going define a grid size of 2000. So it's a 2000 times 2000 matrix, means now I have to calculate 32 megabyte. And as it is a complex number, 64 megabyte. Let's initialize it. And problem itself is quite simple. I time from the beginning of the definitions where I have it in linspace. Then I define a grid. Define the grid to be a complex grid. And initialize the counts. And then it's just the same code I said, and I calculate the time, how long it takes. let's take a look. We can see on the lower left bottom, it pretty much works already at 100%, so powerful loop would not give you even an advantage in this case. Let's see how long it takes. 20 seconds. And I chose the Mandelbrot set because it kind of looks beautiful. And the colors in here is just the evaluation of. So these values, for example, the red ones were for a long period of time still inside the range of, or smaller than 2, but then developed out. If I want to do that now with a GPU, it took 20 seconds. If I want to do that now with a GPU, the only thing I have to do is GPU array.linspace or once GPU array, and all the rest is the same except that I have to gather eventually, because I also want to measure how long it takes to assign it to the memories. And if I run that now, I'm at 0.7 seconds. So it's an improvement of 26, or it's 26 times faster. So for these really simple calculations, GPU excels. And you can even improve it further using so-called GPU array functions. And the pre-initialization is the same, and then it's the function name is array_fun, where I have a function which is a function of x grid, y grid, and the maximum number of iterations. And let's take a look at this function. TMU is not the fastest. This function is generally, as said, it's a function of x and y and the maximum number of iterations. So what this function does, it works on each, or x and y as I give it, as a matrix. But for this function itself, it's an element, or just one element of the matrix. So in this case, I first define the complex value, and then this time I use a while loop, and you see it's not in this case anymore an element-wise multiplication. I don't have a dot here. So it just uses each element individually. But except for this part that I use a while loop, it's pretty much the same. And it stops as well when the absolute is smaller than 2. So in this case, I do not have to go via the whole array, I just go via the small part. And let's run it. And 103%, 103 times faster. Now the question is, could I also use an array function for CPUs? I have looked into it, just the same way how it's described, just feeding instead of GPU arrays, standard arrays. It did not work out. I think that is mostly because this is something which is more directed into GPU calculations. So, what are our limitations? Except that it's not always faster with GPUs. We can't use any built-in functions yet. So if you want to use something of the optimization toolbox, or ODEs, not going to work. So either you write yourself a solver, or you just have to wait. I'm pretty sure it will come. It's just 10 years now, but it's not yet there. Secondly, I worked a bit with really big matrix size. The memory of your GPU becomes your hard limit. You cannot have more on the GPU memory than the GPU memory allows. So you can't use your normal memory. It's only the GPU memory, as the current way it's implemented. This GPU or graphics card has 8 GB, so it's not a big issue. But the commercial lines have up to 24 GB, then it's even less an issue. But keep that in mind. And especially on the consumer cards, the double precision performance is way worse than the single precision. Normally, you would expect that single precision is double, or you have double the performance of double precision, or double precision has half the performance of single precisions. In the case of the consumer market GPU cards, it's not the case. So as far as I know, NVIDIA builds in a hard bottleneck because they have also this commercial line, but compared to a normal graphics card, which costs about range of $300 to $600, the commercial lines is in the range of $2,000 to $10,000. So of course they don't want to cannibalize their own market, hence you can't use it. One thing I haven't mentioned yet, you can also use GPUs for neural network training. And there it excels if you have a lot of number of points. For example, in the range of millions. Then it's multiple faster than CPUs. But then again, it's a question, do you need double precision? If you don't need double precision, GPUs are way faster than CPUs. If you need double precision, it's still faster, but only starting from a certain array size. So, to conclude my talk, both of these methods can improve the performance or reduce the calculation time drastically. As said beforehand, CPU is really good for many iterations, complicated iterations, whereas CPU is if you have quite expensive iterations. No, GPU is for many iterations and CPU for expensive. You have to be a bit careful how you code to reduce communication. MATLAB is giving you a lot of information about that, whether it's annoying what you do or not. You can listen to it, and it normally helps a lot, in my opinion. And important thing as a take-home message as well, what I said now about loop variables and how it should be treated, that is independent whether you use Fortran, C++, C, MATLAB, it's all the same. You just need to understand these concepts. And I use CPU parallelization essentially all the time. Every single simulations I run is with a par-for loop. And GPU simulations not that frequently, I have to admit. Because currently for what I want to use it, it's not yet. I have to write my own Newton solver, and I'm a bit too lazy for that, I have to admit. I can really recommend the webinars of MATLAB. Parts of that was, where I got into was based on a webinar of MATLAB. That is just one link, as I assume you're uploading the presentation anyhow, you have the hyperlink. And based on that, or just Google parallel computing webinar MATLAB. It works really well. One last thing which I wanted to say actually at the beginning, and entirely forgot. To actually be able to run parallelization, what you saw initially, why it took so long, it started a parallel pool. Parallel pools is in MATLAB the saying that it actually should run on parallel. In the case if you do not have one open and you have a par-for loop or anywhere in something where you want to parallelize, it just automatically starts it with the standard conditions. Takes some time, but it works as well. You can also start it manually here on the bottom left. You see these points, and in this case it tells me it's working now for 36 minutes. If it's not used in the next 99 minutes, it shuts down. And if you want to shut it down, you can do that as well whenever you want. Goes pretty fast, and you can also start parallel pools manually, writing parpool. You can also say I want to have a parallel pool with a certain conditions. I want to use these and these cores. So you can have two parallel pools open simultaneously. That works as well. And yeah, 4 workers. Good. That is pretty much what I wanted to say. Thanks for the attention, and I hope I gave you some information about how you simply, really in a simple manner, improve your code in MATLAB. Yes.
Okay. Thank you very much. Do you have any questions? Yes?
Yeah, can you go back to the broadcasting variables that you showed us? I was wondering about the C variable. Is that communicated between the computations? Since it's dependent on the C variable?
No, it's not.
It's not?
It's because pretty much, I mean, if it's associative, pretty much it's independent what the other C is. You can, in this case, it has to be something which has to be independent on the previous value.
Okay, yeah.
So if it's something which is not independent on the previous value, then it's not going to work.
Okay, so since it's associative.
So if we take a look at that, so if I have here C times 2, let's switch to the Norwegian keyboard. I entirely forgot where's the multiplication on an American keyboard. Can anyone help me out?
Just copy the one you have.
Shift 8. So if I have it now in this way, where I have a self-multiplication plus an addition, it will tell me it uses a value set outside of the loop, but could still work. Let's see what comes out. Do I have it still open? Ah, I closed it. The temporary will be cleared at the beginning of each iteration of the par loop. So in this case, it was wrongly assigned. I can't have both. If I have, on the other hand, only this one here, then it's working without any issue. It was from the previous one. Yeah, then it's working. So it has to be associative, and actually in the par for loop description of MATLAB, it pretty much tells you all you can do. You can't do a lot of stuff, but you can do something.
Some more questions?
I saw that you're using an i5.
Yeah.
Have you tested?
Hyperthreading does not help.
That's because I made the experience that when I'm using hyperthreading on an i7 and using the MKL in C++, then it even slows down the program.
I know that hyperthreading does not do anything for these calculations, and honestly I would have been surprised if hyperthreading does anything. That is actually the reason why I use an i5 on my home computer, because the only difference for the i7 would be hyperthreading, and that would have been $100 more, and I say no. So for calculations, hyperthreading does not help you. And the same experience I made as well. Slowing down, hard to say. I haven't compared it on a quad-core. I have not compared it on my dual-core here on the laptop. But for calculations, hyperthreading does not help at all.
More questions?
For CPU arrays, do you have any way like doing like who's looking at how much space you have allocated with all the matrices and everything?
On my, I have not actually looked into that because I barely use it. I have to admit. I use as well MSI Afterburner to tell me how much memory I still have left.
Ah, okay, so it tells you how much.
The MSI Afterburner, but that is an external software. But I mean, it does not tell me directly how much it is. I have not checked whether there's a command like who's, but probably there is one. If not, it's easy to calculate.
Okay, you have more questions? If not, let's take you in again. And please help yourself with some pizza.